Now we've seen all of our ideal configurations with our nice, neat block diagrams, but what does this actually look like when we're talking about circuits? So over the next several videos, that's the question we're going to try to answer by looking at both op-amp circuits as well as discrete circuits with just transistors and resistors. We're going to start with our voltage amp, and remember our voltage amplifier has a series input with a shunt output, so we're talking about our series shunt configuration. And so this circuit here you might recognize from a previous class as being a non-inverting amplifier. And so you might also remember for a non-inverting amplifier in the previous, when we previously analyzed this, we found the closed loop gain, which is equal to the output divided by the input, is equal to 1 plus R2 over R1. And so this was just what we found in a previous class using our ideal op-amp analysis. So let me put in parentheses under here just to be consistent. This was assuming that we had an ideal op-amp. Okay, so now if we consider the general equation, so for the moment, just kind of take my word that this is going to fit our series shunt configuration. But if we think about it, we know it's a voltage amplifier because we have some input voltage and we're getting some output voltage that is a scaled version of that. So let's think about our general equation then for our voltage amplifier. So general equation for our voltage amp. And with feedback, so let me specify here with feedback, what we have is that our closed loop gain, A sub VF, is equal to our open loop gain, A sub V, divided by 1 plus beta V times A sub V. And so remember, beta here is not our current gain of a transistor, this is our feedback transfer function. So now considering this equation, we can, if we remember back from ENG 301, we can say typically this AV value, our open loop gain, is very large, so much greater than 1. So what that means is if we assume that this is a really large value, we can neglect this 1 in the denominator. And so what that means is this AVF becomes AV divided by beta V AV, so the AVs cancel out. And we're left that this is approximately 1 divided by beta sub V. Okay, so now what we can do is we have these two equations for our closed loop gain. So let me get rid of that. So we have this A sub VF here and this A sub VF here. So let's equate the two and then we can figure out what this feedback transfer function beta sub V is. So doing that, we could find that our beta sub V is equal to 1 divided by 1 plus R2 over R1. So simple as that. Okay, so this was kind of just by inspection. We said we know this equation from analyzing it one way. We know this feedback equation for our sort of ideal feedback form. So let's take a closer look and see if we can't figure this out by sort of going back to basics with our op-amp circuit here. So what we have sort of in this area here is our non-ideal op-amp our non-ideal op-amp model. We have some input resistance on the left side, which is typically going to be very large, and we have some output resistance on the output side, which is typically going to be very small. So note, I've also defined our input resistance with feedback and our output resistance with feedback, which are looking in at these dashed lines as indicated by the arrows. And so we're going to take a closer look at the input resistance, but we're not going to look at the output resistance right now. Another thing to notice here is I've also labeled an error voltage and a feedback voltage. So if we come up here, we could actually label these things in this circuit as well. So our error voltage is between our two input terminals of the op-amp, and our feedback voltage is across our resistor R1. So let's see if we can make sense of why that is. Okay, so again, if we're trying to match this with the equation we had above, let's kind of assume this is an ideal op-amp. So we can say typically our R0 is going to be really small. So let's say it's negligibly small, and to be safe, we can just say let's assume it's about 0. And so what that means then is that our output voltage is going to be equal to the value of that dependent source, so just the open loop voltage gain times the error voltage V sub E. Okay, well let's come over here to our left side on our input and see what this error voltage is. So if we do a KVL around this way, what we see is that our error voltage is equal to our input voltage minus our feedback voltage. So we can substitute that in, and what we have then is our output voltage is equal to our open loop gain times our input voltage, the quantity of our input voltage minus our feedback voltage. Okay, so now we want to say, let's assume that our Ri is very large compared to R1. So say assume. And so remember, it's always good to state assumptions. So Ri is very large compared to R1. And so basically what that means is that we can ignore this Ri and we can say pretty much this, any output from here is going this way, and our Ri is not going to be figuring into this voltage divider network. So let's go ahead and get rid of these just for clarity. And so if we ignore that Ri, we're kind of covering this up. We're saying don't focus on that. We see we do just have the simple voltage divider of V naught divided by, dropped across the combination of R1 and R2. So let's write that explicitly down here. And so the voltage then across our R1 value is equal to VFB. So scrolling up just a little bit, keeping in mind this is V naught, that's just a little off the screen. So VFB is going to equal V out times our R1 divided by R1 plus R2. So what we want to do now is we can take this equation for VFB and substitute it in here. So if we do that, we'll get our output voltage is equal to the open loop gain times VI minus V out times R1 divided by R1 plus R2. Okay, so where am I going with all of this though? So if you notice, now in this equation I just have resistor values, open loop gain, and VI and V out. So what we want to do is we can solve for the ratio of the output to the input. So solve for V out over V in, and why do we want to do that? Well, of course this is equal to, by definition, our closed loop gain, or a gain with feedback. So if we end up solving for that, and I'm not going to go through all of the details, what we'll get is that our V out over V in is equal to AV in the numerator divided by 1 plus AV R1 divided by R1 plus R2. And so what we can do then is we can divide everything in this here, the numerator and denominator, by R1. And so why do we want to do that? Well, we're going to see that's going to make it easier to relate to our previous result. So we have our AV here, our 1 here, we're not doing anything with that. And now we're saying let's divide the numerator by R1, so we have AV. Divide R1 by R1, so that becomes 1. And divide R2 by R1, so we have R2 over R1. So we get something that looks like that. Okay, so what we notice then is that this is the exact same form as our ideal feedback expression. So remember here, let's scroll up. Here's sort of our ideal feedback expression. And we notice if we compare these two, we have a beta V that's equal to this. So let's write that down here. So this is the same as our ideal voltage amp with our feedback transfer function beta sub V equals to 1 divided by 1 plus R2 over R1. Okay, so there we've kind of gone through in more detail and shown that we can fit this ideal feedback idea to actual circuits, which of course we would expect, otherwise it wouldn't be of much use. So one other thing we want to look at really quickly is our input resistance. So this when I say input resistance, I'm talking about our input resistance with feedback. So that was our R sub IF. And so let's start with what we had before. We said our input voltage is equal to our error voltage plus our feedback voltage. And we had previously said that our feedback voltage is equal to the output voltage times R1 divided by R1 plus R2. Well, our output voltage we had also previously said was AV times our error voltage. So let's plug that in as well. So VI is equal to our error voltage plus AV times our error voltage, so that's our V out. And now with this R1 divided by R1 plus R2, again, I'm going to divide everything by R1 just to make it easier to sort of relate to that beta sub B we found before. So here we have R2 over R1. So we get something that looks like this. And then, of course, we see we can factor out that V sub E. So let's go ahead and do that here, actually. So we have V sub E times 1 plus AV over 1 plus R2 over R1. Okay, so now coming back to our circuit, if we're looking for this R sub IF, we can say that this R sub IF is equal to the input voltage divided by some input current. Let's call this I sub I, input current. So the ratio of that voltage, that input voltage and that input current are going to give us that input resistance with feedback. Well, if we want to find this input current I sub I, we notice that that's the same current that's flowing here. And so if we know this R sub I value, as well as this epsilon voltage, then we can find I sub I, and then it's just a matter of relating it to our V sub I to get that R sub IF. So let's come down here and put that into sort of equations, because I know that's kind of hard to follow as I'm saying that all. Okay, so our I sub I is equal to V epsilon divided by R sub I. And our R sub I is just going to be some property of our operational amplifier. So then we can come back and we can say, well, this input with feedback is equal to our input voltage divided by our input current. And what we're going to do is we're going to use this equation for our input voltage. So all of that we're going to plug in here. And so what we can see is we're going to be canceling out with that V sub epsilon. We're going to have an R sub I that comes up to the numerator. And then this term in the brackets in the highlighted area above is going to stay. So we have 1 plus AV divided by 1 plus R2 over R1. So we get something that looks like that. And if we use the value of beta that we found before, we see this is R1 times 1 plus beta V A sub V, which whereas before our beta is that 1 divided by the quantity of 1 plus R2 over R1. So again, we see this is the same as for our ideal case. So in the next short video, we're going to look at an example of, well, how do we actually use this? How is it useful to know that beta V is 1 divided by 1 plus R2 over R1? And how can we use that to help us with our analysis? After that, we're going to look at some more combinations of actual amplifiers and relate them to our ideal feedback theory.